Hello everybody, today I'm going to explain the solution to the third problem of the 2024 USACO December contest in the silver division, the problem named 2D conveyor belt. And in this problem we are given an n by n grid where we know for each cell that it can have 5 different values, but at the beginning all cells don't have anything on them, and as we add more values to the given cell, we will basically have more and more cells with different conveyor belts. And in these cells, we want to find out after each of the additions how many cells can still be reached from the end. Because basically, we want to find the minimum number of unusable cells that we can achieve by optimally building conveyor belts, which is equivalent to maximizing the number of cells which have a path to the end destination. And basically, this problem, obviously, when you think about it, it seems at the first glance that you can maybe try to do some sort of a flat fill or even some sort of a traversal to try to find the answer quickly, but the biggest bottleneck is by far the fact that the points are added progressively in the grid and you don't get everything right away. However, when it comes to problems like this, given the fact that we need to know what kind of, let's say, restrictions we have, for example, we can end up in a situation where, for example, if we have a grid like this and for example we have a cycle, let's say that we have a cycle like this, then for example if we have this sort of a cycle, then once this cycle is fully locked, then everything here is also locked even though it's not part of the cycle. And a more interesting thing is that I will make this grid way smaller for the sake of the explanation. The interesting thing is that even if you have uh, a smaller cycle here, I will draw it like this for simplicity, this will still be blocked maybe even before this other cycle is blocked. So there are quite a few cases and it's important to have a very simple implementation in mind, or at least something as simple as possible to avoid spending a lot of time on it. Now, the first idea that works and which came to my mind also, and also when I discussed with other people I know who took the contest, it's something that they came up with, was to actually approach it from the end to the beginning. And when you look at it, this kind of technique is used in different methods, some of them in the silver level, some of them more advanced, but it's good to have it in mind. And basically, the main idea was to reduce this problem to a graph problem, where for every single position you have, so if it has an arrow towards, if it has an arrow from it, then you will create an edge to wherever that cell links to. So for example, from 1, 1, you will make an edge to 1, 2, because it directs to the right. While if there are no restrictions, you would create edges to all sides, because every free cell can reach all 4 sides. And basically, what we want to do is to be able to identify at first how many places are unusable, and over time, as we remove the restrictions, to see how does the answer get lower, because the answer will always get lower. And obviously we can try doing this in of n times m by for each day, where after each day we would reconstruct the entire flat fill process and see how many cells can be reached. It will be important to also take in account the fact that if you have a cycle which is not complete, then it will be the same as removing it from the grid altogether. So again, some optimizations can be found, but again, they wouldn't be able to reach the final answer. However, an idea which worked, and while I implemented it in a much more complicated manner, someone I know implemented it without that much complication, was to actually do it on a step-by-step approach. So at first, what they did was to create the indexes each for each position. So basically, we want to convert it to a graph. And now the answer is obviously at first n times n. And at the beginning, for every single restriction, we want to find basically if the direction, which direction is actually our arrow at. So basically, they converted the arrows and just put them in clockwise order. And basically, we create an edge in this graph between the current point and wherever we would reach next. Obviously, if the point would go to the side of the grid, then it would be the same as having a node 0 that connects everything, and it's actually an important node in our calculations. And basically, as we add the points, at the beginning we will be concerned with the points that don't belong to any query. We want to add edges between these points, and basically between these points what we will do will be some sort of a BFS where we start from the point A. Obviously we would have to make sure that B is already visited, because if not we will just add an edge we will use later. So if B is visited and A is not, then we will add A to the queue. So again, we are working with the indexes of each vertex. And as we add points to the queue, we will look through its neighbors. And if they haven't been visited, we will subtract the answer, because basically this means that once we were able to access A, which is automatically a trigger for a reduction in the answer, we are also going to be able to access other vertices that have been unblocked as a result of unblocking that given vertex. And we will add them to the queue, and this is how we will do this part. Now, given that we trigger a BFS from every single node, you might be wondering why is this not slow? And the reason this is not slow is because we will access every single point only once. And this implies that given that we have at most 4 adjacent positions for each vertex, then the complexity is actually linear in the number of points we have on the grid. So it will be n squared. And obviously, after we do it for the initial points, we also do it in reverse order for the queried points. And after that, you will see that all we have to do is to print the answers at the end of each day and just be done with the problem. And as you can see, the solution, after observing that it's enough to just process the edges you're given, as well as the fact that the free places, and then on a reverse basis from the last to the first query, you will see that it's much easier to get the problem done and obviously have a less complicated solution, which will help you get the full score. Now, this problem is actually, at least in my opinion, more difficult than any of the other two problems. And as far as, let's say, a cutoff goes, if you think at it in terms of, let's say, partials, or if you want to promote but you don't know how to solve the problem fully, it's good when you see something like this, which is more difficult or which seems to be more tedious as far as implementation goes, to think at getting partials. You have here roughly half of the test cases for being able to get a solution working for a small constraint. So again, very valuable points, and it's always good to have these things in mind, even if you can't fully solve the silver contest. If you enjoyed watching this video, please like the video and subscribe to the channel. And also, if you have any feedback or any suggestions, I would be delighted to hear them in the comments. In addition, if your people you know are interested in improving at USACO and they want to me to make more videos, you can also give suggestions in the channel, or you can contact me also for these purposes. Also you can contact me if you check out my other links in descriptions for ways to work more closely to speed up your USACO improvement. Until the next time, good luck with the rest of the contest. Have some happy holidays and see you next time. Cheers.